So students, now our topic is Gauss law and its application. So first we will see Gauss law. What is Gauss law? Gauss law. So see, according to Gauss law, the flux associated with any closed surface is directly proportional to Q net, means total charge enclosed by that surface, right? So I can write it phi equal to Q upon epsilon naught, where epsilon naught is the absolute permittivity. So this is Gauss law. Now what is phi? We know that phi is equal to E dot ds, closed integral of E dot ds, or you can say EDS cos theta. EDS cos theta. Okay, so this is the Gauss law, that the closed integral of EDS cos theta will be equal to Q upon epsilon naught. Phi equal to Q upon epsilon naught, where Q is the total charge enclosed by that surface. Okay, and for derivation of like electric field intensity due to a spherical uniformly charged spherical cell or hollow sphere, so these are the applications of Gauss law. So today we will see it. So the topic is electric field intensity due to a uniformly charged spherical cell or hollow sphere, right? This is the topic. So for this, what we will do, we will take a sphere of radius capital R and a uniformly charged Q is distributed on it. Now consider a Gaussian surface here. This is the Gaussian surface, which is a sphere again, and the radius of this is a small r. Okay, now what we will do, we will take a point P at this Gaussian surface and consider a small area ds in it. Now we will show the direction of electric field here, E. The direction of electric field E and ds will be same here. Now what we can write, consider a spherical cell or hollow sphere of radius r. A uniform charge plus q is distributed on the surface of it. Now consider a Gaussian surface which is a sphere of radius small r. Take a point P on it and select a small area ds. Now if d phi is the flux associated with this small area, ds, then d phi will be equal to E dot ds, means E ds cos theta. Now see, what is theta here? Theta is 0, or you can say the direction of E and ds is same, so I can write it d phi equal to E ds. d phi equal to E ds. Now if phi is the flux, if phi is the total flux, then we can write phi equal to integration of d phi. So what is integration of d phi? It is integration of EDS, right? So I will write it as EDS, integration of ds. Now tell me, what is ds? The area of this sphere Gaussian surface, so I can write it into 4 pi r square, which is the area of this sphere of radius small r. Now this is phi. So by Gauss law, from here I will write by Gauss law, by Gauss law, the flux is equal to the total flux is equal to Q upon epsilon naught, right? So Q is the total charge, Q upon epsilon naught, where Q is the total charge on the surface of this sphere of radius capital R. So what is phi? Phi is E into 4 pi R square equal to Q upon epsilon naught. So I can write it equal to Q upon 4 pi R square epsilon naught. Okay. Now see here, Q, if sigma is the surface charge density, so sigma, if sigma is the surface charge density, so what is sigma? Sigma is equal to Q upon A, or you can write Q upon area. So 4 pi R square, the area of this sphere. So Q equal to, I can write it, Q equal to sigma into 4 pi capital R square. Now put 4 pi R square in place of Q. What you will get? Equal to sigma 4 pi capital R square upon 4 pi small r square epsilon naught. Cancel out this 4 pi and 4 pi. Okay, so E equal to sigma r square upon epsilon naught small r square. This is the electric field intensity. Now see, there are two cases. First one, if small r is equal capital R, then what we will do? First case, when small r is equal to capital R, then I can write it equal to sigma r square upon epsilon naught r square. Cancel out this. So E will be equal to sigma upon epsilon naught. This is the case when capital R equal to small r, right? Means if the point lie here at the surface of the sphere, not the Gaussian surface. Okay, so if is small r equal to capital R, then electric field will be equal to E upon epsilon naught. And if this point P lie inside the sphere, then the electric field will be equal to 0, right? Why? Because inside the conductor the electric field will be 0. So charge is distributed on the surface of the sphere. So inside the conductor, second case, inside sphere equal to 0. This is the second case, equal to 0. Okay. So this is the condition, or you can say the application of Gauss law. Note it down.